Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. High above the Earth, invisible rivers of air race across continents at speeds that would make a Formula One driver envious. These are jet streams, narrow bands of fast-moving air that snake through our atmosphere like cosmic highways carrying weather systems, aircraft, and even volcanic ash across thousands of miles in mere days. Yet for most of human history, these atmospheric superhighways remained completely unknown to us. The story of jet stream discovery begins not in a laboratory or observatory, but in the cockpit of a B-29 superfortress during World War II. In 1944, American bomber crews flying missions over Japan encountered something extraordinary and terrifying. Their aircraft, designed to cruise at 25,000 feet, suddenly found themselves fighting against headwinds exceeding 200 miles per hour. Some bombers flying at maximum throttle were actually moving backward relative to the ground below. Major Ralph Stearley, piloting one of these missions, reported winds so powerful that his aircraft's ground speed dropped to just 14 miles per hour despite flying at full power. The crew watched in bewilderment as their fuel gauges plummeted while barely making progress toward their target. This wasn't just unusual weather. It was something entirely outside their understanding of atmospheric behavior. Japanese meteorologists, led by Wasaburo Oishi, had actually discovered these high-altitude wind streams decades earlier using weather balloons, but their findings remained largely confined to Japanese scientific circles. Oishi's meticulous observations from 1920 to 1925 revealed consistent patterns of extreme wind speeds at altitudes between 30,000 and 40,000 feet. However, the language barrier and limited international scientific communication meant these discoveries went unnoticed by Western meteorologists. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The wartime encounters forced American scientists to confront an atmospheric phenomenon that challenged their fundamental understanding of how air moves around our planet. These weren't just strong winds. They were organized, persistent, and followed predictable patterns that suggested underlying physical mechanisms operating on a planetary scale. Dr. Carl Gustaf Rossby, a Swedish-American meteorologist, became fascinated by these reports and began developing the theoretical framework that would explain jet stream formation. Rossby recognized that these high-altitude wind rivers were manifestations of much larger atmospheric dynamics involving the rotation of Earth, temperature differences between polar and tropical regions, and the complex interplay of pressure systems. The term jet stream itself emerged from the aviation community's need to describe these narrow corridors of extreme wind speed. Pilots noticed that these atmospheric rivers weren't uniform masses of moving air, but rather concentrated streams with distinct boundaries, much like water jets from a garden hose, but stretched across continents and moving at altitudes where the air is too thin to breathe. What makes jet streams particularly intriguing is their role as atmospheric engines that drive weather patterns across entire hemispheres. These invisible highways don't just carry air, they transport energy, moisture, and weather systems with incredible efficiency. A storm system caught in a jet stream can traverse the entire continental United States in just 3 days, bringing dramatic weather changes to millions of people. The discovery of jet streams revealed that Earth's atmosphere operates more like a vast three-dimensional ocean than the simple layered system previously imagined. These findings would revolutionize meteorology, aviation, and our understanding of climate patterns, setting the stage for modern weather forecasting and atmospheric science. Understanding jet streams requires diving into the fundamental physics of our rotating planet and its atmosphere. These atmospheric rivers don't form randomly. They're the inevitable result of Earth's rotation, temperature differences, and the laws of fluid dynamics operating on a planetary scale. The primary driver of jet stream formation is the temperature gradient between Earth's polar and equatorial regions. The sun's energy strikes the equator nearly perpendicular to the surface. Throughout the year, while polar regions receive sunlight at increasingly oblique angles. This creates a temperature difference that can exceed 60 degrees Celsius between tropical and Arctic air masses. As warm equatorial air rises and moves poleward, it encounters the Coriolis effect, a phenomenon caused by Earth's rotation that deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection isn't a force in the traditional sense, but rather a consequence of Earth's rotation beneath moving air masses. Imagine standing on a spinning playground merry-go-round and throwing a ball straight across to a friend. From your perspective on the rotating platform, the ball appears to curve away from its intended path. Similarly, air moving poleward from the equator gets deflected eastward, while air moving equatorward gets deflected westward. The mathematical description of this phenomenon involves the Coriolis parameter, which varies with latitude. At the equator, the Coriolis effect is zero, while it reaches maximum strength at the poles. This variation creates a fundamental asymmetry in atmospheric circulation that helps explain why jet streams follow the paths they do. Temperature gradients also create pressure differences that drive air movement. Warm air is less dense than cold air, creating lower surface pressure in tropical regions and higher pressure in polar areas. However, at altitude, this relationship reverses. The warm tropical atmosphere extends much higher than cold polar air, creating higher pressure aloft in tropical regions and lower pressure at the same altitude over polar areas. This pressure differential creates a horizontal pressure gradient force that drives air movement from high to low pressure regions. Combined with the Coriolis effect, this results in the characteristic eastward flow of jet streams in both hemispheres. The conservation of angular momentum plays a crucial role in jet stream acceleration. As air moves poleward and Earth's radius effectively decreases beneath it, the air must spin faster to conserve angular momentum, similar to how figure skaters spin faster when they pull their arms closer to their body. This principle helps explain why jet streams can reach such extraordinary speeds. Jet streams typically form along boundaries called frontal zones, where cold polar air meets warm tropical air. These boundaries aren't smooth transitions, but rather sharp discontinuities that can extend vertically through the entire troposphere. The resulting wind shear, the difference in wind speed and direction at different altitudes, creates the narrow, concentrated flow patterns characteristic of jet streams. The thermal wind relationship, a fundamental principle in atmospheric physics, describes how wind speed changes with altitude in response to horizontal temperature gradients. In regions where temperature changes rapidly over horizontal distances, winds must increase significantly with altitude to maintain atmospheric balance. This explains why jet streams are strongest at the tropopause, the boundary between the troposphere and stratosphere. Rossby waves, large-scale atmospheric oscillations named after Carl Gustav Rossby, add another layer of complexity to jet stream behavior. These waves develop when the jet stream encounters obstacles like mountain ranges or encounters variations in surface heating. The resulting wave patterns can persist for weeks, creating blocking patterns that dramatically affect regional weather. The mathematics governing jet stream formation involves solving the primitive equations of atmospheric motion, which account for the conservation of momentum, mass, and energy in a rotating fluid system. These equations, while conceptually straightforward, require sophisticated numerical methods and supercomputers to solve for realistic atmospheric conditions. Modern understanding reveals jet streams as manifestations of baroclinic instability, i.e., fundamental atmospheric process, where potential energy stored in horizontal temperature gradients converts to kinetic energy of motion. This energy conversion process helps maintain the jet streams while simultaneously mixing warm and cold air masses, moderating Earth's temperature extremes. The challenge of mapping invisible atmospheric rivers required ingenuity, persistence, and technologies that pushed the boundaries of 1940s meteorology. Scientists faced the daunting task of tracking phenomena that existed 6 to 8 miles above Earth's surface, moving at speeds exceeding 200 miles per hour, and following paths that changed seasonally and even daily. Weather balloons became the primary tool for jet stream exploration. These latex spheres, filled with hydrogen or helium, could carry instrument packages called radio sondes to altitudes exceeding 100,000 feet. As balloons ascended, radio sondes transmitted real-time data about temperature, humidity, pressure, and wind speed back to ground stations using primitive radio technology. The radio sonde system, developed in 1935 by Robert Bureau in France, revolutionized upper atmosphere research. These devices, roughly the size of a small book, contained meteorological sensors, a radio transmitter, and a parachute system. Ground stations could track balloon positions using radio direction finding equipment, calculating wind speeds and directions at various altitudes. Early balloon launches revealed that jet streams weren't uniform tubes of fast-moving air, but rather complex three-dimensional structures with cores of maximum wind speed, surrounded by regions of gradually decreasing velocity. Scientists discovered that jet streams typically measured 100 to 300 miles wide and 1 to 3 miles thick, with wind speeds often exceeding 150 miles per hour at their cores. Dr. Jerome Namias at the U.S. Weather Bureau began systematically mapping jet stream positions using data from weather stations across North America. His analysis revealed that the Northern Hemisphere typically contained two major jet streams: the subtropical jet, located around 30 degrees north latitude, and the polar jet, positioned between 50 and 60 degrees north latitude. The subtropical jet formed due to temperature contrasts created by the Hadley cell circulation, where warm air rises at the equator and descends around 30 degrees latitude. This jet stream remained relatively stable in position throughout the year, flowing from west to east at altitudes between 25,000 and 35,000 feet. The polar jet proved more variable and dynamic, forming along the polar front where cold Arctic air meets warmer air from middle latitudes. This jet stream's position could shift dramatically, sometimes dipping as far south as the Gulf of Mexico or retreating north of the Canadian border. Its strength and position directly influenced weather patterns across entire continents. Seasonal mapping revealed fascinating patterns. During winter months, temperature gradients between polar and tropical regions intensified, strengthening jet streams and shifting them toward the equator. Summer weakened these temperature contrasts, causing jet streams to weaken and retreat poleward. This seasonal migration explained long-observed patterns in storm tracks and weather system movement. International cooperation became essential for comprehensive jet stream mapping. The newly formed World Meteorological Organization coordinated balloon launches and data sharing between countries, creating the first global picture of upper atmosphere circulation. Weather stations from Alaska to Argentina, from Norway to New Zealand, contributed observations that revealed jet streams as truly planetary phenomena. Scientists discovered that jet streams followed wave-like patterns around the globe, typically containing 4 to 6 major waves at any given time. These Rossby waves, with wavelengths spanning thousands of miles, determined where jet streams would bring storm systems, fair weather, or blocking patterns that could persist for weeks. The development of upper air weather maps transformed meteorology. These charts, showing wind patterns at various altitudes, revealed jet streams as the organizing principle behind much of Earth's weather. Meteorologists learned to track storm systems by following jet stream patterns, dramatically improving weather forecasting accuracy. Mountain ranges emerged as crucial influences on jet stream behavior. The Rocky Mountains, Himalayas, and other major topographic features created standing waves in jet stream flow, similar to how rocks in a river create downstream turbulence. These orographic effects helped explain regional climate patterns and seasonal weather variations. By the 1950s, regular jet stream analysis became standard practice at weather bureaus worldwide. Meteorologists created standardized symbols and analysis techniques for mapping these atmospheric rivers, establishing protocols that remain in use today. The invisible highways of the sky had finally been charted, revealing Earth's atmosphere as a complex, interconnected system driven by fundamental physical principles. Jet streams function as Earth's primary weather engines, steering storm systems across continents and determining whether regions experience drought, flooding, heat waves, or Arctic blasts. These atmospheric rivers don't merely transport weather, They actively create and intensify weather systems through complex interactions with surface conditions and other atmospheric layers. The relationship between jet streams and surface weather begins with their role as storm highways. Cyclonic systems, areas of low pressure that bring clouds, precipitation, and winds, typically form along jet stream boundaries where contrasting air masses meet. The jet stream's rapid horizontal motion creates areas of divergence aloft, where air spreads apart and rises from the surface below. This rising motion creates surface low pressure, drawing in surrounding air and initiating the cyclonic circulation. That defines storm systems. As these developing storms encounter the jet stream, they become entrained in its flow, accelerating eastward at speeds that can exceed 50 miles per hour. A storm system born over the Pacific Ocean can cross the entire North American continent in just 3 to 4 days. The jet stream's wave-like pattern determines where storms will track and intensify. When the jet stream develops deep southward, dips called troughs, it creates powerful areas of upward motion on the eastern sides of these features. Storm systems encountering these regions undergo rapid intensification, sometimes developing into major winter storms or severe thunderstorm complexes within 24 hours. Conversely, northward bulges in the jet stream called ridges create areas of sinking air and high pressure at the surface. These ridging patterns suppress storm development and can persist for weeks, creating blocking patterns that dramatically alter regional weather. The infamous heat wave that struck Europe in 2003 resulted from a persistent ridge that deflected the jet stream far to the north, allowing hot, stagnant air to dominate the continent for months. Jet stream speed variations play crucial roles in weather development. When the jet stream accelerates as it rounds a curve, similar to water speeding up when flowing through a narrow channel, it creates areas of speed divergence that enhance upward motion and storm development. These jet streaks, regions of maximum wind speed within the broader jet stream, often trigger the most intense weather events. The polar vortex, a large area of low pressure and cold air surrounding Earth's poles, maintains a complex relationship with jet streams. When the polar vortex remains strong and well organized, the polar jet stream flows in a relatively straight path around the Arctic, keeping cold air locked at high latitudes. However, when the polar vortex weakens or becomes distorted, the jet stream develops large amplitude waves that can bring Arctic air far southward into populated areas. The phenomenon known as sudden stratospheric warming can dramatically disrupt this system. During these events, temperatures in the stratosphere can increase by 50 degrees Celsius within days, weakening the polar vortex and causing the jet stream to develop extreme wave patterns. These disruptions can trigger severe cold outbreaks across North America and Europe, sometimes lasting for weeks. Seasonal variations in jet stream behavior create predictable climate patterns. During winter, strong temperature gradients between polar and tropical regions intensify jet streams and shift them toward the equator. This brings storm tracks southward, explaining why Mediterranean climates experience wet winters and dry summers. The summer retreat of jet streams toward the poles creates the dry season in these regions. The jet stream's interaction with ocean temperatures adds another layer of complexity. Sea surface temperature patterns, such as those associated with El Niño and La Niña events in the Pacific Ocean, can alter atmospheric heating patterns and modify jet stream positions. These teleconnections can influence weather patterns thousands of miles away from the original oceanic disturbances. Research has revealed that jet streams also play crucial roles in transporting moisture across continents. Atmospheric rivers, narrow corridors of concentrated water vapor, often align with or interact with jet streams, creating precipitation patterns that can bring beneficial rains or devastating floods, depending on their intensity and duration. The vertical structure of jet streams influences their weather-making potential. Strong jet streams with well-defined cores can efficiently ventilate developing storm systems, removing air from their upper levels and allowing continued intensification. Weak or poorly organized jet streams provide less ventilation, limiting storm development even when other conditions favor weather system formation. Understanding jet streams as weather engines has revolutionized forecasting. Modern meteorologists use jet stream analysis as a primary tool for predicting storm tracks, intensity changes, and the timing of weather pattern shifts, enabling increasingly accurate forecasts that save lives and protect property. The discovery of jet streams revolutionized aviation almost overnight, transforming flight planning from a relatively simple exercise in navigation to a complex three-dimensional chess game played against invisible rivers of air moving at incredible speeds. Pilots and aviation planners quickly realized these atmospheric highways could either be powerful allies or formidable adversaries. Initially, jet streams presented more challenges than opportunities. Early encounters, like those experienced by World War II bomber crews, demonstrated how these high-altitude winds could turn routine flights into fuel-consuming ordeals. A Boeing Stratocruiser flying from New York to London might find its 8-hour flight extended to 12 hours when flying against a strong jet stream, forcing unplanned fuel stops and schedule disruptions. However, aviation pioneers soon recognized the flip side of this equation. Flying with a jet stream could dramatically reduce flight times and fuel consumption. The same New York to London route that took 12 hours against the jet stream could be completed in just 6 hours when riding the atmospheric river eastward. This realization sparked a revolution in flight planning and aircraft routing. Captain L. Ray Jeppesen, already famous for his navigation charts, became one of the first aviators to systematically study jet stream utilization. Jeppesen worked with meteorologists to develop routing procedures that would allow pilots to find and use these atmospheric highways effectively. His approach required detailed analysis of upper-level weather patterns and careful coordination between meteorologists and flight dispatchers. The introduction of commercial jet aircraft in the 1950s magnified both the challenges and opportunities presented by jet streams. Early jets like the de Havilland Comet and Boeing 707 operated at altitudes where jet streams were strongest, making their effects impossible to avoid. Flight crews had to master new techniques for navigating in and around these atmospheric rivers. Trans-Pacific flights revealed jet streams' most dramatic effects. The Great Circle route from Tokyo to Los Angeles crosses regions where winter jet streams can exceed 250 miles per hour. Flights traveling eastward with these winds could complete the journey in under 10 hours, while westbound flights against the same winds might require 14 hours or more. Airlines began employing specialized meteorologists called flight dispatchers who analyzed jet stream patterns to optimize routing. These professionals developed sophisticated techniques for finding the most efficient paths through the three-dimensional maze of atmospheric rivers. A typical trans-Pacific flight might climb or descend several thousand feet multiple times to take advantage of favorable winds or avoid adverse ones. The development of stepped climb procedures emerged directly from jet stream optimization. Instead of climbing directly to cruising altitude, aircraft would ascend in stages, spending time at intermediate altitudes where jet stream conditions were most favorable. This technique required careful coordination with air traffic control and precise fuel calculations. Jet stream turbulence presented new safety challenges. The boundaries of these atmospheric rivers often featured severe, clear air turbulence that could injure passengers and crew without warning. Pilots learned to recognize atmospheric conditions associated with jet stream turbulence and developed procedures for avoiding or minimizing encounters with these invisible hazards. Weather radar, initially designed to detect precipitation, proved ineffective against clear air turbulence associated with jet streams. This limitation led to the development of new detection technologies and forecasting techniques specifically designed to identify areas of potential jet stream-related turbulence. Modern aircraft now carry sophisticated weather radar systems capable of detecting atmospheric disturbances that create turbulent conditions. The fuel efficiency implications of jet stream utilization became enormous as fuel costs increased. A wide-body airliner could save thousands of gallons of fuel on a single trans-Pacific flight by optimizing its route relative to jet stream positions. Airlines invested heavily in meteorological services and flight planning systems to maximize these savings. International aviation cooperation became essential for effective jet stream utilization. Flight information regions around the world began sharing detailed upper-level wind data, enabling more accurate routing decisions. The development of global weather communication networks allowed real-time updates of jet stream positions and intensities. Modern flight management systems now incorporate jet stream data directly into their routing calculations. These computers can analyze thousands of possible flight paths, considering factors such as jet stream positions, intensities, and forecast changes throughout the flight duration. The result is optimized routing that can save hours of flight, time, and significant fuel costs. The advent of satellite-based wind measurements in the 1970s provided unprecedented accuracy in jet stream analysis. Satellites could track atmospheric motion across entire ocean basins, providing data unavailable from ground-based weather stations. This information enabled even more precise flight planning and routing optimization. Today, virtually every commercial flight above 30,000 feet considers jet stream effects in its routing. What began as an unexpected obstacle discovered by wartime bomber crews has evolved into a fundamental tool of modern aviation, enabling faster, more efficient flights that connect our global economy. Modern atmospheric science has unveiled jet streams as far more complex and influential phenomena than early researchers could have imagined. Advanced satellite technology, supercomputer modeling, and sophisticated measurement techniques have revealed intricate details about these atmospheric rivers and their connections to global climate systems. Satellite-based observations revolutionized jet stream research beginning in the 1970s. The first weather satellites could only provide basic cloud imagery, but successive generations developed increasingly sophisticated instruments for measuring atmospheric motion, temperature profiles, and wind speeds at various altitudes. The Advanced Microwave Sounding Unit aboard polar orbiting satellites can now measure atmospheric temperatures with precision better than 1 degree Celsius. Doppler wind LiDAR technology, deployed both on satellites and ground-based systems, provides detailed three-dimensional maps of atmospheric motion. These instruments use laser pulses to measure the movement of tiny particles suspended in the atmosphere, creating detailed profiles of wind speed and direction from surface to stratosphere. The European Space Agency's ALICE satellite, launched in 2018, represents the most advanced space-based wind measurement system ever deployed. Supercomputer modeling has transformed understanding of jet stream dynamics. Modern weather models divide the atmosphere into millions of grid boxes and solve fundamental equations of motion for each box every few minutes of simulated time. The most advanced models, running on computers capable of performing quadrillions of calculations per second, can simulate jet stream behavior with unprecedented detail and accuracy. The Global Forecast System, operated by the National Weather Service, processes over 40 billion observations daily, from satellites, weather balloons, aircraft, and surface stations. This massive data integration effort creates four-dimensional maps of atmospheric conditions that reveal jet stream structures invisible to earlier generations of scientists. The models can track individual jet streaks as they develop, intensify, and dissipate over periods of days to weeks. Research aircraft equipped with specialized instruments provide ground truth for satellite observations and model predictions. The National Science Foundation's Gulfstream Phi research aircraft can fly directly through jet streams at altitudes up to 51,000 feet, measuring temperature, humidity, wind speed, and atmospheric chemistry with laboratory-grade precision. These missions have revealed fine-scale structures within jet streams that satellites cannot resolve. Isotope analysis of water vapor transported by jet streams has opened new avenues for understanding atmospheric circulation. Different water sources have unique isotopic signatures, allowing scientists to track moisture transport pathways across continents. This technique has revealed how jet streams connect distant regions, carrying water vapor from tropical oceans to continental interiors thousands of miles away. Climate model simulations extending centuries into the future reveal how jet streams might respond to changing global conditions. As polar regions warm faster than tropical areas, the temperature gradients that drive jet stream formation are weakening, Some models predict more meandering jet stream patterns with deeper north-south excursions, potentially leading to more persistent weather extremes. The discovery of multiple jet stream layers has complicated traditional understanding of atmospheric circulation. In addition to the well-known tropospheric jets, scientists have identified jet streams in the stratosphere and mesosphere. The stratospheric polar night jet, forming during winter months, can reach speeds exceeding 300 miles per hour and influences ozone distribution in the upper atmosphere. Machine learning techniques applied to decades of atmospheric data have revealed subtle patterns in jet stream behavior that escaped traditional analysis methods. Artificial intelligence algorithms can identify precursor conditions that lead to specific jet stream configurations, improving long-range weather forecasting and climate prediction capabilities. The connection between jet streams and ocean currents has emerged as a crucial component of Earth's climate system. Jet streams influence evaporation patterns over oceans, affecting sea surface temperatures and ocean circulation. Conversely, ocean temperature patterns can modify atmospheric heating and alter jet stream positions, creating complex feedback loops that operate over multiple timescales. Research into the Arctic's changing climate has revealed dramatic shifts in polar jet stream behavior. As Arctic sea ice diminishes and polar temperatures rise, the temperature gradient between Arctic and mid-latitude regions weakens, potentially making the jet stream more prone to large amplitude waves that can bring extreme weather to populated areas. High-resolution atmospheric chemistry models have shown how jet streams transport pollutants, volcanic ash, and other atmospheric constituents across vast distances. The 2010 eruption of Eyjafjallajökull volcano in Iceland demonstrated how jet streams could carry volcanic ash across Europe, disrupting air travel for weeks and highlighting the need for better atmospheric transport modeling. Paleoclimate research using ice cores, tree rings, and other proxy data has extended jet stream analysis thousands of years into the past. These studies reveal that jet stream positions and intensities have varied significantly over geological timescales, providing context for understanding current and future changes in atmospheric circulation patterns. Modern research continues, revealing new aspects of jet stream behavior, from their role in transporting atmospheric moisture to their influence on air quality and their connections to phenomena ranging from El Niño to the Indian monsoon, demonstrating that these atmospheric highways remain active frontiers of scientific discovery. The future of jet streams stands at the intersection of climate science, technological advancement, and human adaptation to a changing atmosphere. As Earth's climate system evolves, these atmospheric highways are responding in ways that will reshape weather patterns, aviation operations, and our fundamental understanding of planetary circulation. Climate models consistently predict significant changes in jet stream behavior as greenhouse gas concentrations continue rising. The most profound impacts stem from Arctic amplification, the phenomenon where polar regions warm faster than the global average. As temperature differences between polar and tropical regions diminish, the thermal gradients that drive jet stream formation weaken, potentially leading to slower, more meandering atmospheric rivers. Research led by Dr. Jennifer Francis at Rutgers University suggests that weakening jet streams develop larger amplitude waves, creating more persistent weather patterns. These slower-moving, wavier jet streams can lock weather systems in place for extended periods, potentially increasing the frequency and duration of heat waves, droughts, and flooding events. The European heat wave of 2023 and the persistent winter storms of 2021 may represent early manifestations of this changing behavior. Advanced climate models project that subtropical jet streams may strengthen and shift poleward as tropical regions expand due to warming. This migration could alter precipitation patterns across Mediterranean climates, potentially bringing wetter conditions to some regions while creating drier conditions elsewhere. California's water resources, Australia's agricultural regions, and Mediterranean Europe could all experience significant changes in seasonal precipitation patterns. The aviation industry faces both challenges and opportunities from evolving jet stream patterns. Stronger subtropical jets could provide more powerful tailwinds for flights between Asia and North America, potentially reducing flight times and fuel consumption. However, more variable and unpredictable jet stream positions could complicate flight planning and increase the risk of severe turbulence encounters. Next-generation aircraft design increasingly considers jet stream optimization. The proposed supersonic passenger aircraft incorporate advanced flight management systems capable of real-time jet stream analysis and routing optimization. These systems could automatically adjust flight paths to maximize tailwind benefits while avoiding areas of severe turbulence, potentially making supersonic travel more efficient and comfortable. Artificial intelligence and machine learning are revolutionizing jet stream forecasting. Deep learning algorithms trained on decades of atmospheric data can identify subtle patterns that human analysts miss, improving predictions of jet stream, position and intensity changes. Google's DeepMind has demonstrated weather forecasting systems that can predict jet stream behavior with accuracy comparable to traditional numerical weather models while requiring significantly less computational power. The development of quantum computing promises to further enhance atmospheric modeling capabilities. Quantum computers could potentially solve the complex equations governing atmospheric motion with unprecedented speed and accuracy, enabling detailed jet stream forecasts extending weeks or months into the future. This capability could transform long-range weather forecasting and seasonal climate prediction. Satellite technology continues advancing our ability to observe and understand jet streams. The upcoming generation of hyperspectral atmospheric sounders will provide three-dimensional wind measurements with spatial resolution approaching 1 kilometer. These observations will reveal jet stream structures and dynamics at scales previously impossible to observe, potentially uncovering new aspects of their behavior. Stratospheric jet streams are emerging as increasingly important components of the climate system. The polar stratospheric jets influence ozone distribution and can affect surface weather patterns through complex coupling mechanisms. Understanding these interactions becomes crucial as stratospheric conditions change. Due to greenhouse gas increases and ozone recovery, urban heat islands and land use changes are creating local modifications to jet stream behavior. Large metropolitan areas can alter atmospheric heating patterns enough to influence jet stream positions on regional scales. As global urbanization continues, these effects may become more pronounced, requiring new approaches to weather forecasting and climate modeling. The potential for weather modification technology raises questions about intentional jet stream manipulation. While current capabilities remain limited, future technologies might enable limited steering or modification of jet stream patterns. Such capabilities would raise profound questions about international cooperation, environmental ethics, and the governance of planetary-scale atmospheric interventions. Ocean-atmosphere coupling models reveal complex interactions between jet streams and marine systems. Changes in jet stream patterns can alter ocean evaporation rates, sea surface temperatures, and marine ecosystems. Understanding these connections becomes crucial for predicting impacts on fisheries, coastal communities, and ocean carbon absorption. Educational initiatives are preparing the next generation of atmospheric scientists to tackle these challenges. Universities worldwide are developing interdisciplinary programs combining atmospheric physics, computer science, and climate modeling. These programs emphasize international cooperation and data sharing, recognizing that jet streams represent truly global phenomena requiring coordinated research efforts. The future of jet stream science lies in integration, combining observations from multiple platforms, models of varying scales and complexities, and interdisciplinary approaches that consider atmospheric, oceanic, and terrestrial interactions. As we continue unveiling the mysteries of these atmospheric highways, we gain not only scientific understanding, but also the tools necessary to adapt to our changing planet. These invisible rivers of air, discovered through wartime necessity and mapped through decades of patient observation, continue revealing new secrets about our dynamic atmosphere, promising discoveries that will reshape our understanding of Earth's climate system for generations to come.